Alright, so in this video I'm going to be explaining another approach for domain adaptation. We are using in the unsupervised setting, and the tool that we use is graph convolutional network. Our model is a graph neural network. So this article in 2020 from Monash University. So graph convolutional networks have achieved impressive success in many graph-related analytics tasks. However, most graph convolutional networks only work in a single domain, incapable of transferring knowledge from to other domains due to challenges in both graph representation learning and domain adaptation over graph structures. In this paper, we present a novel approach, unsupervised domain adaptive graph convolutional networks for domain adaptation learning for graphs. To enable effective graph representation learning, we first develop a dual graph convolutional network component. We jointly exploit local and global consistency for feature recognition. An attention mechanism is further used to produce a unified representation for each node in different graphs. To facilitate knowledge transfer between graphs, we propose a domain adaptive learning module to optimize three different loss functions, namely source classifier loss, domain classifier loss, and target classifier loss as a whole. Thus, our model can differentiate class labels in the source domain, samples from different domains, the class labels from the target domain respectively. Experimental results on real-world datasets in the node classification task validate the performance of our method compared to state-of-the-art graph neural network algorithms. So we can move from source domain to a target domain by a good adaptation. Of course, in the source domain, we have labeled data, but in the target domain, there is no labeled data, so it's fully unsupervised. So there are four contributions. We present a novel unsupervised graph domain adaptation. We propose an effective graph convolutional network to solve it. We propose a novel method to integrate local and global consistency with an attention mechanism to learn effective node embedding across networks. We design a new way to exploit source information and target information with different loss functions so that domain invariant and semantic representations can be effectively learned to reduce the domain discrepancy for cross-domain node classification. We evaluate our method on real-world datasets, and the results demonstrate that the proposed model outperforms the baseline methods. So we have a graph, some nodes, some edges, and we have X and Y. And Y is always a label matrix. So our source domain could be like this, and target, there is no label in target. So we only have our input data. So these are input, but only the source domain has the labels. So given an unlabeled target network and a fully labeled source network, the cross-domain node classification is to build a classifier to accurately classify the nodes in the target network with the assistance of the fully labeled source network. However, this is a challenging task due to the lack of labels for G sub T. In order to learn the better representation of each node, we employ dual graph convolutional networks to capture the local and global consistency relationship of each graph. We develop an intergraph attention approach to automatically determine the weights of the source and target graph representations from the local and global graph convolutional network layers. To enable cross-domain classification, we advocate a domain adaptive learning approach to train three classifiers. The first one is source classifier and aims to minimize the classification loss on the source domain data. The second one is domain classifier, and the domain adversarial loss is utilized to enforce the differentiation between the source and target domains. The third one is target classifier, and there is no label in the target domain, and entropy loss is placed on the target classifier. So by doing so, the domain adaptive learning can maximally utilize the domain information and target domain information to learn domain invariant and semantic representations effectively to reduce the domain discrepancy for cross-domain node classification. So the methodology is like this. First, we have node embedding module, because in order to encode the semantic information of each node, the node representation learning procedure consists of two graph neural networks. We have local consistency network. By directly utilizing the graph convolutional network, we formulate it as a type of feed-forward neural networks. Then we have global consistency network. So in addition to this local convolutional network, local graph convolutional network, which defines the adjacency matrix A, we introduce a PPMI convolution-based method to encode the global information, which is denoted as a matrix. Before obtaining the matrix P, we first calculate the frequency matrix F using the random walk. Random walks have been used as a similarity measure for a variety of problems in recommendation, graph classification, semi-supervised learning. Here we use the random walk to calculate the semantic similarities between nodes. We then calculate P and explain why it leverages knowledge from the frequency to semantics based on F. Finally, we define the P-based graph convolutional function. So the global behavior can be obtained by these random walks. So the Markov chain describing the sequence of nodes visited by a random walker is called a random walk. If the random walker is on node x sub I, so condition on initial state x sub I at time t, we define state as s sub t is equal to x sub I. And the transition probability of jumping from current node to one of its neighbor is just this probability. And it's related to your adjacency matrix. But we also have point-wise mutual information, which is very important, because after calculating the frequency matrix F, the ith row in F is the row vector F sub I, and the jth column is the column vector F sub I corresponds to a node X sub I, and F sub j corresponds to context Cj. The contexts are defined as all nodes in X. The value of an entry is the number of times that X sub I occurs in context Cj. So we can calculate PPMI matrix P. But since our node embedding module consists of two networks, in addition to conv-A, which is based on similarity defined by adjacency matrix, another network conv-P is derived from the similarity. So this is the neural network. And D is just for normalization. So applying diffusion based on such a node contextual makes it ensure global consistency. Additionally, by using the same network structure as conv-A, the two can be combined very concisely. Therefore, the source and target graphs are fed into the parameters shared node embedding module to land representations. So this is the overall architecture of proposed unsupervised domain adaptive convolutional network. You have source graph, you have target graph, there are shared parameters, and you have adjacency matrix for source and target, and then you have the attributes, and then you have source classifier, target classifier, but we also need this domain classifier, and we use domain adversarial loss that I've explained several times. And then intergraph attention. So the model is a little bit complex. So we use the original input, x of source, x of target, as the key of the attention mechanism. So we then perform attention on each domain output. The two attention coefficients, attention S and attention K, are computed by attention function for each domain. So K here is just the outputs from source domain S or target domain T. Could be anything, K, S, K, T. So K could be S, K could be T, depending on the input. And then we normalize it. It's just, the rest of that is just a softmax layer. But here is very important. We can get the final output just as a linear combination of them, because some of them care about local and global things, and also we have target and source. But to better learn and knowledge transfer across different domains to assist in node classification tasks, our proposed model consists of an adversarial module, a source classifier, as well as target classifier working together to learn both class discriminative and domain invariant node representations, thus enabling classifying nodes in the target network. The overall objective is this. So we have source classifier, this is source classifier. Then we have domain classifier loss, and then we have target. And we have source classifier loss, as I said. Here we just model it as simple as this, because it's just a cross entropy loss. And so we have two more loss, as I said. For domain adaptation, again, it's a cross entropy domain classifier loss, but we use it in adversarial setting. And the target is, again, similar to source, it's just cross entropy. And this is the summary of what I said. Obtained embedding for source domain and target domain. Learn output embeddings. Learn source classifier, domain classifier, target classifier, and backpropagation through all of these. Oh, they also use early stopping, which is very interesting. But for methods, we go from source to target domain, and you see different scores across six cross-domain tasks. 1, 2, 3, 4, 5, 6. There are deep walk is a very important method. Graph Sage, I think I've explained it in a lecture on graph neural networks playlist. And this one, so you can see sometimes it's high, sometimes it's low, depending on source and target. So if source is C and target is A, it becomes this. And if we change these, it becomes A, the source becomes A, the target becomes C, then it's almost the same. So A and C are very critical because others are much better. That's why the average is low, just because of this one and this one. It reduces the performance.